Welcome everyone. In this part of the video, I am going to start a new chapter, equilibrium. Firstly, the equilibrium means it is a state at which the concentration of reactants and the products do not change with time. Whenever the concentration of reactant, suppose we have a reaction like concentration of reactant is getting converted into product, and if the state is come like the concentration of the reactant terms is not changing with the concentration of a product term, so there must be a sign, and that state or that sign is known as equilibrium. So the equilibrium is the state where the concentration of reactant and the concentration of product do not change with time. It means whenever we consider the concentration in form of concentration of reactant and product in form of rate, because we know something which is changing with respect to time, that is known as rate. So whenever the rate of forward reaction, the reaction which is taking place in forward direction here, the rate of this reaction when the reactants are getting converted into the product, the rate of that reaction must be equal to the rate of the backward reaction. Backward reaction means the rate or the reaction when the products are getting converted into the reactants again. So the equilibrium is a state where the rate of the forward reaction must be equal to the rate of the backward reaction. So this can be proved with the help of this example. Here in this example, the formation of ammonia is taking place when N2 in gaseous state, nitrogen in gaseous state plus 3 moles of H2 in gaseous state, it is combining with each other and providing 2 moles of NH3. At the same time, the 2 mole of NH3 is producing N2 and 3 moles of H2 here. So this is a state, and here it is, this sign is known as equilibrium, and for this particular state, the rate of the forward reaction, the rate of N2 and thrice of H2 is equal to the rate of the twice of NH3 molecule. It means the rate of the forward reaction equal to the rate of the backward reaction. So this is the equilibrium. Now this can also be explained with the help of this graph also. In this graph, suppose we are plotting a graph between rate of a reaction and time. So initially the rate of the forward reaction will be higher. Initially it is getting converted into the product. So the rate of the forward reaction means N2 and H2 when it is providing NH3. This is the forward reaction. The rate of this reaction initially it will be higher with respect to with the same time. But at the same time the rate of the backward reaction will be the lower one. And what will happen as the time will pass on, the rate of the forward reaction will decreases and the rate of the backward reaction at the same time will increases. But there will be a time will come or a point will come, or after increasing the time with after this point, the concentration of the forward reaction as well as the backward reaction will not change by changing the time. So it means the rate of forward reaction now equal to the rate of the backward reaction. Initially जो forward reactions हैं, जो reactants हैं, जब वो product form कर रहे हैं तो initially उनका rate ज़्यादा होगा because product का formation हो रहा है. लेकिन अगर हमारी स्टेट इक्विलिब्रियम की है, हमें एक ऐसी स्टेट मिल रही है कि प्रोडक्ट्स दोबारा फॉर्म कर रहे हैं रिएक्टेंट्स, तो उस रिएक्शन को हमने बैकवर्ड रिएक्शन नेम दिया. सपोज अगर हमने टाइम यहाँ पे सपोज 0 सेकेंड अगर हम टाइम लेके चलें, सो फॉर 0 सेकेंड रेट ऑफ फॉरवर्ड जब तक रिएक्टेंट्स ने रिएक्ट करना शुरू करा है या रिएक्ट नहीं हुआ है 0 टाइम पे, या यू कैन टेक इट एज 1. सो उस टाइम पे फॉरवर्ड रिएक्शन का रेट 1 होगा और बैकवर्ड रिएक्शन का फॉरवर्ड रिएक्शन का रेट हाई होगा बैकवर्ड रिएक्शन के रेट से. लेकिन एज सुन एज द टाइम इज पासिंग देयर विल बी अ स्टेट विल कम, एक स्टेट आएगी या एक टाइम का एक पॉइंट आएगा आफ्टर विच द कॉन्सेंट्रेशन ऑफ द रिएक्शंस बोथ फॉरवर्ड एज वेल एज द बैकवर्ड रिएक्शन विल बी इक्वल. एंड आफ्टर दैट टाइम अगर हम टाइम को चेंज भी करते हैं तो फॉरवर्ड और बैकवर्ड रिएक्शन का जहां रेट इक्वल हो गया, इट मीन्स वो स्टेट को हम बोलेंगे इक्विलिब्रियम स्टेट. Now in equilibrium there is a law. This law is known as law of mass action. So the definition or the statement for the law of mass action is the rate of a chemical reaction is directly proportional to the rate of molar concentration of reactants at a constant temperature at any given time. It means according to law of mass action, whenever a reaction is taking place, any reaction which is taking place, the rate of that chemical reaction is directly proportional to the product of molar concentration. This we have to keep in mind. The chemical reaction, the rate of that reaction must be equal to the product of molar concentration of the reactants at a constant temperature at any given time. So suppose we have an equation A and B, these are the reactants and these are providing products. So for this particular chemical reaction, the rate of reaction will be R. This can be represented as R. So according to the statement of mass action, this R is directly proportional to the product of molar concentration of reactants. So the reactants are A and B, and it is the rate is directly proportional to the molar concentration of A and B. Here this bracket is used to express the concentration of the species or to express the concentration of reactants or products sometimes. Here this A and B are the reactants, so whenever they are present in the square bracket, so it is termed as the concentration of A and B. So if we will replace this proportionality sign, so there will be a constant term, and this R is equal to some constant K into concentration of A into concentration of B, because that is the product of molar concentration. That's why we have placed here a multiplication sign. Similarly, if our reaction have some stoichiometric coefficients, like our reactants 2 mole of A are used and 3 mole of B are used, and they are producing products. So for that reaction, the rate of the reaction according to law of mass action, it is directly proportional to the molar concentration of A and B, the molar concentration of the molar concentration of reactants, and the reactants are A and B. And in addition to this statement, the stoichiometric coefficients of the reactant must raise to the power of the concentration term. These are the stoichiometric coefficient. For A, the stoichiometric coefficient is 2, so it must be raised to the power here. And for 3, the stoichiometric for B, the stoichiometric coefficient is 3, so it must be raised to the power of the concentration. Now similarly, if you remove the proportionality sign, you will get R is equal to K, concentration of A square, concentration of B cube. Now from here come to the next. Whenever our reaction is in equilibrium, this law of mass action is for any chemical reaction. Whenever a reaction is taking place, this is for all the chemical reaction. Now suppose if our reaction is in equilibrium, so there must be an equilibrium constant which will arise there. So suppose our reaction is A plus B, these are the reactants, and in equilibrium they are providing C plus D as a product. So it means whenever the reaction is in equilibrium, so the rate of this A forward reaction, the rate of formation of C plus D through this forward reaction, this upward side, this forward reaction, it must be equal to the rate of this backward reaction, or the rate of the formation of A plus B through C and D. Now for that, the rate of the forward reaction according to law of mass action, for this equilibrium condition, what will be the rate of forward reaction? For simplicity, if I write for forward reaction, our forward reaction is A plus B is producing C plus D. This is our forward reaction. So for forward reaction, according to law of mass action, what will be the rate? Rate will be directly proportional to the product of molar concentration of the reactant. Here the reactants are A and B, that's why it is written rate is directly proportional to concentration of A into concentration of B. And if we remove the proportionality sign, so there must be a constant, and because as I have already told, it is a forward reaction, so this constant term is known as Kf here. So R is equal to Kf, or molar concentration of A into molar concentration of B. Similarly, for the backward reaction, as our backward direction is this, backward reaction is this. So in backward reaction, what is happening? C plus D are now act as a reactant, and now A plus B will act as a product for backward reaction. So for backward reaction, according to law of mass action, the rate of reaction for backward reaction must a constant. This is the constant for the backward reaction, Kb, into molar concentration of the products. Molar concentration, product of molar concentration of reactants. So the product of molar concentration or the multiplication of molar concentration of the reactants are C and D for the backward reaction. So the molar concentration of C into the molar concentration of D from here. Now as our reaction is in equilibrium, so at equilibrium we know the rate of the forward reaction is always equal to the rate of the backward reaction. So what is the rate which we have find out for the forward reaction? It was Kf, concentration of A into concentration of B, and that must be equal to the rate of backward reaction, and that is Kb, concentration of C into concentration of D. Suppose on rearranging this equation, suppose all the constant term one side, then Kf will be equal to Kf upon Kb will be equal to concentration of C into concentration of D divided by concentration of A into concentration of B. This will be the rearrangement. This will be the reaction after rearrangement. Or if this is a constant term, if this constant term is represented by a whole constant term K, then it is K is equal to concentration of C into concentration of D divided by concentration of A into concentration of B, where this K, this constant K, is termed as equilibrium constant. This is called equilibrium constant. So whenever our reaction is in equilibrium, then the rate of the forward reaction must. And suppose if we have a reaction line, the reactants A and B having some stoichiometry terms, A has some stoichiometry coefficient small a and B has some stoichiometry coefficient small b, and they are in equilibrium with the product C and D, and this C has a stoichiometric term C and this D has some stoichiometric term small d. According to law of mass action, the equilibrium constant or the representation of equilibrium constant for this reaction will be and the equilibrium constant is termed as Kc here, because we are considering the concentration term for that. So Kc will be equal to concentration of the product, concentration of C into concentration of D, and their stoichiometric terms must raise to the power according to the law of mass action divided by concentration of the reactant terms A and B, and their stoichiometry terms will be raised in power. So this is the formula Kc, equilibrium constant for this equation. Now suppose equilibrium constant whenever all the reactants and products, they are present in gaseous phase. So the equilibrium constant for a gaseous system, suppose our reactants, these are present in gaseous phase, and as well as our products are also present in gaseous phase. The whole system is a gaseous system. So for that, in place of concentration, we use the partial pressure of reactants as well as the partial pressure of products. So here the equilibrium constant will be written as Kp, and this P stands for pressure or the pressure of the gaseous system, and wherever we are using the concentration term, then this C stands for concentration. Equilibrium constant in terms of concentration is Kc, equilibrium constant K in terms of partial pressure is termed as Kp. So whenever all the reactants and products are in gaseous phase, then Kp must be equal to partial pressure of C, this partial pressure of C raised to the power C, because C is the stoichiometric coefficient, and similarly the partial pressure of D is written as Pd here and the stoichiometric term in the power also, and similarly Pa is the partial pressure of reactant A and the stoichiometric term is small a, Pb is the partial pressure of reactant B and the stoichiometric term as small b here. Now we will check a relation between the equilibrium constant in terms of partial pressure Kp and equilibrium constant in terms of concentration Kc. We will check a relation between Kp and Kc. Suppose a reaction is given A plus B having stoichiometric coefficient small a and small b. In equilibrium they are producing C and D, and they have a stoichiometric coefficient as a small c and small d. So whenever we are taking the condition for a concentration term, so whenever we are talking about the concentration term, in place of concentration term, the equilibrium constant will be Kc, and that Kc must be equal to, according to law of mass action, concentration of the product, and their stoichiometry terms will raised in power divided by concentration of reactant in multiplication, and their stoichiometry terms will raised in power, like this. Suppose this is equation number 1 which we have to use, and suppose these all are gaseous in nature, all the reactants and products are gaseous in nature. So in terms of pressure, the equilibrium constant is called Kp, and for Kp the representation or the expression will be partial pressure of C into partial pressure of D, and both stoichiometry terms of both will raise to the power, like this. Similarly, the partial pressure of A into the partial pressure of B, and their stoichiometry terms will raise to the power. And suppose this is equation number 2. These will be the relationship. Now as we have assumed that all the reactants and the products are in gaseous phase, suppose we are taking the gaseous substances for the ideal gas. Suppose we are assuming that all the gases are ideal in nature, and according to the ideal gas equation, we know that ideal gas equation is PV equal to nRT. This is the ideal gas equation. Suppose all the gases which are used in reactants and product side, these all are ideal in nature. So according to ideal gas equation, PV equal to nRT, and from here if I rearrange the value n upon V into P is equal to n upon V into RT, and we know a term where P is the pressure, or we can say the partial pressure also. This n upon V, number of moles of the gas upon the volume of the gas, must be equal to the concentration of the gas, or we can say it is equal to the concentration, or C, of the gas. You can write here concentration of gas also. So P is the partial pressure, so we can write it as P is equal to CRT also. Now this is the partial pressure of gas. Suppose I have to write down the partial pressure for gas A. For gas A, what will be the partial pressure? It will be written as PA, and the value of PA will be the concentration of C, concentration of the gas A. Concentration of gas A, it can be written as Ca into RT, or PA must be equal to, concentration is represented in the square bracket, or concentration of which? Concentration of gas A, or concentration of this reactant A here. So PA equal to concentration of A into RT. Similarly, as I write here PA, we can write the partial pressure of gas B also. So the partial pressure of gas B will be equal to concentration of gas B into RT, where R and T are the constant. Similarly, we can write it as partial pressure of C, can be written as partial concentration of C into RT, and partial pressure of gas D can be written as, it can be written as concentration of D into RT. These are the values of partial pressure. Now as we have to put these values in equation number 2 from here, suppose this is equation number 2. So to again put on putting the values, putting these values of partial pressure of A, partial pressure of B, partial pressure of C, and partial pressure of D in equation number 2. Now what will we get? Equation number 2 is Kp, partial pressure of C. What is the partial pressure of C? It is concentration of C RT whole power C. Similarly, what is the value of concentration, partial pressure of D? It is concentration of D RT and whole power small d divided by the concentration of A RT, partial pressure of A RT whole power A partial pressure of B, RT whole power small b. This is the value of equation number 2 and this is the value of Kp from here. So on rearranging this equation, what we will get? We will just get Kp will be equal to, suppose on taking some constant or some common terms outside, so concentration of C into concentration of D to the power D, and here RT to the power C and RT to the power D. These both are RT and RT are the common term and their powers must be added then, because they have a same common terms in the base. So RT to the power C plus D divided by the same thing will happen in the denominator, concentration of A to the power A into concentration of B to the power B, and RT is common again and their power will be A plus B, must be A plus B from 11. If this is the condition, now in the next step on rearranging the equation, we will get concentration of C, concentration of D to the power D, concentration of A to the power A, and concentration of B to the power B. And here again the base are same, and if same base are dividing, then the powers will get multiplied by each other. So RT. So for the same base, when the same base are present at the denominator, then the powers will get subtract from each other. So RT and the power will be C plus D minus A plus B from here. Now on rearranging the equation again, and if we come to our equation number first, from our equation first, and our equation first was Kc is equal to concentration of C, concentration of D to the power D, concentration of A to the power small a, and concentration of B to the power small b. So here in this equation number 3, if we replace Kc by these terms, so the new equation will be Kp will be equal to Kc. From here Kp will be equal to Kc and RT and the whole powers, because these C plus D and A plus B, these are the stoichiometry terms, or we can say the number of moles of the C plus D are the number of moles or the summation of number of moles of product. A plus B are the summation of number of moles of the reactant terms. So number of moles, and this is the number of moles of reactant minus the number of moles of the product. This is the number of moles of product minus the number of moles of reactant. So this can whole be written as delta N, where delta is the change in number of moles, delta N is called change in number of moles. So from here we get a value, and the value is Kp is equal to Kc RT to the power delta N, where delta N will be termed as change in number of moles, change in number of moles, or change in number of moles means change in number of moles. This delta N can be the number of moles of product side minus the number of moles of the reactant side. So it is because our products are C and D, so the number of moles of C and D are small c and plus small d will be the number of moles of product, minus the number of moles of reactants are A and B, so it is small a plus small b. So delta N must be equal to C plus D minus A plus B. So this is delta N, and it is the relation between Kp and Kc. Here Kp is always equal to Kc RT to the power delta N. Now let's take an example. Suppose I have an example, and I am taking an example of N2 at gaseous state and 3 of H2 at gaseous state, and in equilibrium they are producing twice of NH3 again in gaseous state. So if we have to find out the value of Kp and Kc, and if we have to stabilize the relation between Kp and Kc for this reaction, so firstly we have to calculate the value of delta N. Now let's calculate the value of delta N, because as I already told, delta N is number of moles of the product. Here number of moles of product is 2, because there is only one product is present here, so, and the stoichiometry terms of the product or the number of mole of NH3 is 2. Number of mole of product minus number of moles of the reactant. Here the number of reactants are 2, so the number of moles of reactants will be 1 for N, because stoichiometry term of N2 is 1, plus number of moles of H2 are 3, so it is 1 plus 3. So delta N comes to be 2 minus 1 plus 3 is 4. 2 minus 4, it is coming to be minus of 2. So when we have to stabilize our relation between Kp and Kc, so Kp will be equal to Kc RT to the power minus of 2. Similarly, express or write the expression of Kp and Kc for these two reactions as well, in the same way as we have done for N2 plus 3 of H2 gives twice equilibrium sign twice of NH3. So similarly you can do, or you can develop a relation between these two reactions as well. Now the next is units of equilibrium constant. There are the units of equilibrium constant. So the very first condition for the units of equilibrium constant, when the total number of moles of products is equal to the total number of moles of the reactant. It means the number of moles of product side, it means suppose these are the reactants and products, so the number of moles of the product side here, it suppose it is 1, and the number of moles of the reactant is also 1. So if the condition is like that, the number of moles of the product is equal to the number of moles of reactant. Suppose I have taken an example here, it is H2 plus I2. In equilibrium it is providing twice of HI or 2 moles of HI. So according to the concept of equilibrium constant, or we can write it as Kc or K as well. So the Kc will be equal to, according to law of mass action, it will be equal to concentration of the product HI to the power stoichiometry term will raised in the power, and here stoichiometry is 2, or the number of mole is 2, divided by the concentration of the reactant, it is H2, and the concentration of the another reactant I2, it is written here. So as we know, the concentration, because concentration is equal to number of mole upon volume. So the unit of concentration, because the unit of number of mole is represented as mole and the unit of volume is as liter. So the unit of concentration will be mole per liter or mole liter inverse. So the for concentration of HI, the unit will be mole liter inverse, but whole power 2 here. And similarly, the concentration of H2 will be mole liter inverse, and concentration of I2 will be mole liter inverse. As we can see here, the total the number of moles of the product, number of moles of the products are 2. For it, we have to calculate the value of delta N. The number of moles of the products are 2 minus the number of moles of the reactant, 1 of H2 and 1 of I2. So delta N is coming to be 2 minus 2, it is 0. It means that whenever the number of moles of the product is equal to number of moles of the reactant, here it is, you can see here, at that time it is mole 1 power and mole and mole inverse will get cancelled out. So for that, the value or the unit of equilibrium constant, there is no unit. Equilibrium constant has no unit for such condition, wherever the number of moles of the product side is equal to the number of moles of the reactant side. Now similarly, when we the next condition, suppose when the number of moles of the products is different than the number of moles of the reactant, then what will happen? Now let's check. Here it is, the example is N2 plus 3 of H2 is providing 2 of NH3 in equilibrium. Now for this equation is, suppose we have to write down the value of Kc. So Kc will be equal to concentration of NH3 whole power 2, because the stoichiometry is 2, and the concentration of N2 and concentration of H2 to the power 3. Similarly, if I have to write down the units for concentration, so for NH3, the NH3 square, the unit will be mole liter inverse square, divided by, for N2 it is mole liter inverse, into it is mole liter inverse cube. This is the representation of this. So on rearranging this particular equation, we will get 1 power will get cancelled out with this, 1 mole inverse will get cancelled out with this. So the term or the unit of Kc will be 1 upon mole liter inverse square from here, or you can write it as liter inverse square. So when this will come in the numerator, it will come as liter square, and mole per liter square per mole square, this will be the unit. If both the terms are different, if both here the number of moles of the products are 2 and the number of moles of the reactants are 1 plus 3. So number of moles of the product are 4, whereas number of moles of the reactants are 4, whereas the number of moles of the reactants are 2 only. So in this case the equilibrium constant will have some value. But whenever the number of moles of reactant and number of moles of products are equal, at that time the equilibrium constant will not have any value. So that's all for today. Do some questions related to this, and we will meet with our new topic in our new video. Thank you. Keep watching.